Hi everyone, and welcome to the Cybersecurity Sauna. Thanks for joining us for another session where we sweat out the hot topics in security. Welcome to all our listeners, and be sure to follow us on Twitter at #CyberSauna. AI and machine learning are shaping our online experience, from product recommendations to customer support chatbots to virtual assistants like Siri and Alexa. These are powerful tools for enabling business, but powerful doesn't mean perfect. Today's guests, data scientist Samuel Marchal and security consultant Jason Johnson, are here to talk about some of the machine learning security issues and how to address them. Welcome to the show, guys.
Hi, Janne.
Hi.
You guys say that machine learning in its current state presents some security challenges. What are those challenges?
The one that I really focus on is sort of a lot of variations really on sort of this concept of these systems looking like they've gotten the right answer, but for reasons that don't really generalize well, don't really hold up out in the real world. So you can have something that has, superhuman performance on some task, but then turns out to be relying on completely ridiculous rules that break down as soon as, say an attacker or just maybe even random chance out in the real world breaks some of those assumptions in a way that wasn't anticipated by the developers.
Can you give me like an example of something you've seen where that happened?
I think maybe the easiest one to understand is this concept of adversarial perturbation, which is, very fancy words, but it's a really common attack where you can very slightly modify the images that maybe a facial recognition scanner or something like that is operating on to give totally ridiculous results. Like you can, for instance, 3D print a baseball that an image classifier will look at and say, this is 100% certainly an espresso.
Okay, yeah.
Even if it's on the catcher's mitt, even if there's context that says it's a baseball, it'll still be misunderstood.
Right. I've seen those pictures where there's like a couple of squiggly lines on a picture, and the AI says, "Yep, that's a cat. That's what a cat looks like." So that's what you're talking about.
Exactly.
Exactly. And actually, I totally agree with Jason. And so one of the main reasons for this is that, in contrast with a normal program where you code basically the behavior, here the behavior is basically learned from data. And how this is learned, basically you don't exactly program the way that it will learn. So it will grab anything in the data that can be meaningful to make its decision. But this is often not how a human would analyze an image and make the decision on what is in the image. The algorithm will just try to optimize this function and will take whatever features in this image that help it make the best decision. And that's why actually it may be completely fooled by small perturbations, because it will put its attention on the wrong features that do not lead to this good decision that it must make.
So is this a problem that happens because of the way that these machine learning algorithms learn things? So it's just something that happens, sort of, it takes a wrong turn somewhere and that gets multiplied over and over again. So it's not something somebody's done to sort of mislead the AI.
Yeah, it's inherent. Like you cannot force an algorithm to learn exactly what you want to learn. You just have basically an objective. It tries to optimize the objective and it takes the path that he wants to optimize this objective. And it's often what you don't expect.
The real challenge is often that the objective you wrote into your code isn't exactly what you wanted. And if you knew exactly what you wanted, you wouldn't need to use machine learning to get your answer in the first place.
Exactly.
So the security concerns we're thinking about is that, even though you might get an answer, you don't understand how we arrived to that answer. And you're not sure if the route taken was sort of correct, in that all steps made sense.
Exactly.
Yeah, exactly. And I think, this comes actually from this big involvement of data, basically at the input to train the algorithm and also at inference when you make those prediction and recommendation. And I think this is the main difference between machine learning model, machine learning algorithm, and traditional program. This increases the attack surface and creates new ways to attack systems, in my opinion. And these new attack vectors, let's say, cannot be dealt with traditional security. And you need new solution actually to address those new attack vectors.
There are some different ways you can do these training exercises, these design your models, architectures, and use different choice of algorithms and all these technical details that are less susceptible to these kinds of mistakes, that give you more control over what sorts of features your model is learning from. But the problem is they perform worse. And they are maybe more understandable, but they can't get the kinds of hype generating, market moving, really spectacular results that people are talking about.
Right. Okay, so I can get how the machine learning algorithm might go astray when it's trying to figure out the best way to go someplace. But there have also been instances where the attackers have tried to sort of twist the machine learning algorithm on purpose. Why would somebody do something like that?
So I think you refer maybe to these poisoning attacks where you would compromise either the training data or the training algorithm of the model such that it will learn in a wrong manner and basically provides wrong prediction later when it's at inference. So I think there are many motivations for this because machine learning models are included already in many applications, and they will be included in more and more applications. So for instance, if we take some example of security applications, so machine learning models are already used in spam detection, fraud detection, like for payment fraud detection, for malware detection. So if you have some machine learning components that are part of your detection system, an adversary will basically try to compromise this system such that it will circumvent detection. So if you can compromise the model that makes the decision, is that a fraud or not, or is that a spam or not? So if you can compromise this model so that it will render wrong decisions, well, the adversary will just circumvent the detection and achieve his first purpose. So committing fraud or like sending a spam email that will get through to your mailbox. Then there are also other motivation for this. Now we see a lot of machine learning models that will be used in maybe those autonomous vehicles. So you can just launch an attack against a model that is used for image recognition in a self-driving car just to cause disruption.
Right, yeah.
Maybe a concrete example. Somebody's developing a new machine learning model to do malware detection. What they're going to do is they're going to take data from VirusTotal and they're going to say, we're going to train our model to recognize things that VirusTotal lists as malicious because, the experts have already taken a look at that and all that sort of thing. And that methodology sounds reasonable, right?
Sure.
So now as an attacker, what you might do is let's say you've heard about this marketing company and you said, I am going to build the malware that gets by this. What you do is you cook up some totally benign strings, some gibberish in text that doesn't mean anything, but you're going to put it in your malware. And you submit 15 million different examples of totally benign software that does nothing wrong, nothing harmful, that happens to have those strings embedded in it. Now, if it's a naive model, it's going to learn to recognize those strings as signs of benign software. And when it gets your malware that happens to also have those strings in it, then it's going to classify it as totally safe and harmless, regardless of what it actually does.
All right. So you called this data poisoning attack. So basically, that's me going on Amazon and looking at children's books and looking at horror movies and doing that a million times today, so that the algorithms think that people who like children's books like horror movies as well. What other kinds of attacks are there?
At least I consider that there are 4 main attacks on machine learning models. So first is this poisoning and backdooring attack where you compromise the training data or the training of the model to compromise the integrity of the model in the end. The second is happens at inference time, which is this model evasion attack where so the model is totally normal, but then you would craft inputs at inference that will get wrong predictions or wrong recommendations. Then the third attack is called maybe data inference attack. And in this case, you don't target the model, but you target the training data the model was trained with. So basically, during the training process, the machine learning model will learn about this training data. And if this training data is privacy sensitive, so actually, you can recover some part of this training data just by having access to the model. So it compromises basically the confidentiality of the data a model is trained with, and you can extract some information just by interacting with the model. Finally, the last attack is the called model stealing attack. So where here we consider that the machine learning model has a value, okay, and an attacker would try to replicate this model and use it basically for free, or maybe propose it to customers. So also just by interacting with the model, making queries, getting predictions, you can reconstruct a model that behaves in a similar manner as a model that you want to steal. And then you can get this model for pretty low cost and not having to basically pay the provider of the original model that trained that model. So those 4 attacks are, I think the most prominent that we have to care about talking about machine learning.
So are all these things done sort of through the user-facing interface as if I was using that script for whatever, or does the hacker need sort of access into the back-end systems or something like that?
It depends. I know that's not a very satisfying answer.
It's a consultant answer.
In a lot of cases, access to the back end will make the attack a lot more efficient, a lot more reliable. Mm-hmm. But in some cases, it's also possible to reconstruct your... you can use these model recovery attacks that we already mentioned to recover a model that looks like that behaves in the same way. And then you can use that model to construct the other kinds of attacks against the original one that you've copied.
How does that work?
The idea is you'll first you'll build this copy, and what you'll do to do this is use whatever user interface you've got. Yep. And you'll train your model to just give the same answers as
the original model.
Exactly. And you won't necessarily know everything about what the original model is doing, but you'll build one up that behaves in the same way on the same kinds of inputs.
Sure.
And once you have that, then you can, for instance, craft your evasion techniques against that.
Yeah. Okay.
Yeah, and then chances are they'll also work against the original model, even though you never had access to it.
So I'm building like an offline lab where I can practice my techniques.
More or less, yeah. It's very It's a pretty similar concept.
Yeah. Okay.
Yeah. So I think actually most of the attacks that are really happening now against machine learning models are done in this black box fashion, where you don't have any understanding of how the model is doing, but you just try to guess, and actually you can trick it. And I think there are actually examples of poisoning attacks that really work like this. And so for instance, Google has been reporting that they have this spam filter in Gmail, and regularly they see attempts of poisoning this spam filter, just getting a lot of submissions of benign emails that are actually labeled as spam, such that you will just degrade the accuracy of the spam filter, and exhaust a bit the user that will get all its legitimate email classified as spam, and maybe deactivate the spam filter. And then, the attacker wins because his spam will just go through if he deactivates the spam filter. So I think there are some examples of these attacks, and here I think the attackers don't know at all what kind of machine learning model they use to train this spam filter, but they just try. They put some wrongly labeled data, and it works.
Yeah, okay. Just do something and see if it works.
Yeah, exactly.
Any other examples, Jason, that you want to tell us? Cool stories of AI misbehaving?
I think a good one that comes to mind is this is just an academic study, a proof of concept, not like somebody out in the wild doing something crazy evil, but the idea that they came up with was, can we recover credit card numbers from language models that were trained on data that happened to include those credit card numbers from like data dumps or from like random internet searches or whatever? And the answer is yes. They took the if you remember Enron, their internal emails leading up to their business closing were released publicly. Yeah. And they've become actually a really popular data set for training language models on email because they're huge, they're natural language, and they're all well classified and that sort of thing. So they trained up a language model just on those emails. And then they tried to recover credit card numbers by seeing which 16-digit numbers were predicted as most likely. And because the language model had to memorize those in order to do well in training, it generally predicted a few specific numbers that were actually in the original data set.
So you'd be asking the AI sort of like, give me any number, any 16-number string that you can think of, and it would just go to this first one, where that would happen to be a credit card number because that's a number it kept seeing over and over again.
Exactly. And in the real world, this would, of course, you could just search the emails with Enron because they're public. But if you had a data set that was trained on something private, and you had the developers thinking to themselves, look, it's a machine learning model. It's super opaque. Everybody's always complaining about that. They're not going to be able to recover this data. Then that's how it would be. That's how you could use the sort of attack to recover credit card numbers against that.
Oh, that's
or social security numbers and that sort of thing.
So what does that mean? That means that as I'm developing sort of my machine learning algorithm, I have to be like very careful about sort of what sort of information I'm exposing it to.
Yep.
Yes.
So, okay. So on this topic, like if I'm now a company that is considering taking AI into use, what are some of the other things that I need to consider? Like we just established that you have to sort of look at the data you're training it on, make sure there's nothing there that you'd want to leak inadvertently. What could the company stand to lose if their AI application is successfully attacked, I guess, is what I'm asking.
Imagine the scenario where the system always makes the wrong decision.
Mm-hmm.
That's your worst case scenario, more or less.
I like that.
A good reason to keep that in mind as well is that a lot of these systems will attack themselves in their own way. The models can learn solutions to problems you didn't want it to solve that are just related to what it was what you tried to construct it for. Mm-hmm. There's sort of a concept called specification gaming. Again, very fancy word. But if you're deploying these systems, you have to sort of treat them as a sort of a monkey's paw that's going to do technically what you asked for, but never what you wanted. And you have to sort of approach it with that kind of skepticism.
It's one of those genie situations where be careful what you wish for.
Exactly. So, for instance, we've had an example of a model trained to recognize cancer as skin growths. And it actually showed like 95% performance. It was super useful. And then when somebody took a closer look at it, they realized that what it was actually doing was recognizing whether there was a ruler in the picture or not, because that was apparently very common in the data set.
Of course.
Because if somebody has gotten a ruler out to measure the growth, that implies that it's probably actually malignant.
Oh, that's insane. Any other sort of advice, Samuel, for example, you'd want to give to companies who are taking AI into use? We talked about sort of making sure your data contains nothing that you wouldn't want to leak. What's something else that's common?
Well, first, I would advise to apply some of the basic security practices into data science. For instance, software engineers are trained actually for secure coding, but data scientists typically aren't. And I think this would be a good thing to train data scientists and data engineer for secure coding. And also, when you plan to develop a machine learning based system, just perform threat modeling on it. So this process of threat modeling the machine learning model and being aware of those machine learning specific threats, machine learning specific attack vectors that are different from traditional attack vectors against system. So I think this would be one of the first things to implement in the development and lifecycle management of machine learning models. But I think, in more than 90% of cases, this is not applied. So I think this would be a big step.
Yeah, traditional security people need to learn about AI security, and AI security data scientists need to learn about traditional security.
Yes, they must be put together, those people.
Perfect. That makes sense. Yeah. I guess what I want to know is machine learning algorithms sometimes find routes that we didn't think they would to get to the result. So is there a way to sort of look at what the algorithm is learning and sort of tell if it's going in a good direction or in a bad direction? Like I've seen cases where people like in those autonomous vehicle races, their car just does something weird and somebody asks like, why did it do that? And they're like, I don't know. So can you tell if it's going wrong or right, the learning?
There are a few questions there. So, of course, I think explainability is desirable for machine learning. And there is, a whole line of research that try to explain the decision of even the most complex models by trying to explain basically locally some decision. But this won't prevent attacks.
Yeah,
because basically, when we talk about evasion attacks, those adversarial examples are something that never happens like in the real world. Like clearly, they are synthetically generated. This is something you cannot expect to see, and I think not something that you can stop if you don't explicitly try to stop them, like try to prevent them, because. Yeah, they are just generated using some clever algorithm, And you have basically to have the same intuition to create those examples in order to prevent and to protect from them. So explainability, of course, is desirable, but it won't like secure your machine learning model completely. It may help, of course. It may help.
Exactly. You can get more robust, but you can't get completely perfect. The reality of the situation is that if you want to have a machine learning model that avoids some particular pitfall, you have to know what that pitfall is, and you have to go out of your way to actually prevent it from happening. So you need to know in advance which ways these things can go wrong, or you have to train them up and see how they go wrong in order to understand what's going on. And this is, I think, one of those challenges related to the fact that if we knew how to actually do these things correctly, if we knew what the right answer was, we wouldn't need the machine learning model to find the answer in the data in the first place.
Yeah, okay. I guess that makes sense. Maybe what I'm wondering is, like, in traditional security, we have these best practices, like you should be doing this, you shouldn't be doing that. Is there anything like that in like hardening AI or machine learning models against attacks? Is there like any best practices that you can do to sort of hope that it won't go very, very badly wrong?
I would say no.
Okay. I would say yes, actually.
Nice.
There are a few things that I would say most developers really should be doing, if it's applicable to their model, but it is always going to be a matter of expertise for making that judgment call of, is it applicable? So there's, for instance, a concept called differential privacy, which is designed to make sure that no single piece of information in your data set is determinative of any given answer at time of inference. And the reason this creates privacy is it means it's not as practical to do some of these data reversal attacks in the first place. The problem is this naturally impacts the quality of the model, and it's not a complete panacea against privacy attacks either. It has a very narrow definition of what privacy means.
Yeah, so actually, I agree with you, Jason, but that's the thing, that everything that seems to be a trade-off. And that's why I don't know if you can just give recommendations, because I think it's use case specific, and you have to know what you want to optimize in the end.
Sure.
Because like also we studied, for instance, this vulnerability to poisoning and backdooring attack. And we see that basically simpler models are more vulnerable to this basic poisoning attack that degrade the accuracy as a whole, while they are more complex models are more resilient to these attacks. But on the other hand, like the simpler models are very resilient to backdoor attacks, but more complex models are very vulnerable. So like here is just, you have to know what you want to protect against. Do you use a simple model or a complex model to be resilient against poisoning or backdoor attack? And well, also you have to just consider your primary objective to have a good accuracy on this classification task. So yeah, I think you have all these parameters, and it's something that you need to tune and choose. Like, do you want privacy? Do you want robustness to evasion attack? Do you want robustness to poisoning attack? So I think all of this must be considered, and there is no just single answer. Do this, do that, and you will have a good model.
Yeah, okay. That makes sense. So, as you can tell from my questions, I'm struggling to sort of wrap my head around this AI stuff, and I think a lot of people are. Like, that's why we're talking about all these very concrete, tangible examples of what does that look like? How do you mean these things? Is there anything sort of that you guys feel that people should know about? I'm not even just maybe talking about the man on the street. I'm talking about people who work, for example, in security. Is there anything you feel that security people should know about AIs, but they maybe currently don't?
AI models are vulnerable. And they may not be aware.
That goes on a t-shirt. Yeah.
This is a complete tangent, but I've always been a fan of a mug that I've actually got right here that basically says deep neural networks. It has a flowchart from untrustworthy data through a bunch of question marks down to infallible results.
Okay, yeah, that makes sense.
But the real answer is that I think a lot of the major differences between traditional security and machine learning is that in the domain of machine learning, everything is probabilistic. You don't necessarily have guarantees about cause and effect like you do in a traditional security situation.
Mm. But that's hard. Like if I'm the CISO of a company and my propeller heads are talking about machine learning this and AI that, I'd want to sort of weigh in with some security advice, but nothing I've learned in school and in my career sort of works here in this domain. So what am I to do?
Well, I think that's something that really can secure machine learning models more is basically restrict access to data, being it like training data or like the inference data. So a model, I think a machine learning model is pretty secure if it works in a closed loop, like in the back end, where it takes input that are produced inside your organization. And like at inference, it's the same. It takes input produced inside the organization that are very, very reliable, that you can trust. And the predictions are used in this closed loop. But I think most of the machine learning application that we envision now and that we use them for, like, being it recommendation system, is just, data from everywhere, like thousands or millions of users it's processed. And then it makes this recommendation based on this data also from thousands or millions of users. So, of course, those models are very exposed. But if you have some use cases where you use those machine learning models in this very closed loop, like in the backend, I think they are much less vulnerable, of course, if they are not exposed like this.
To add to that, I think the two questions I'd come back to the technical folks with are, what are you doing to ensure things are safe even if this model fails? And who's responsible if the model fails? Yeah. I know that's a harsh question, but when you've got humans who are doing these tasks, it's the human who's responsible, right? You can talk to the human, you can ask what their decision process was, you can figure an answer out. It's not about assigning blame, and it doesn't have to be, but you do still need to know how this is going to shake out in terms of responsibility.
How is that not assigning blame? We've just taught like an entire industry not to blame people for their mistakes, and now you're sitting there asking, like, whose fault is it when this inevitably fails?
The goal there shouldn't necessarily be to assign blame to somebody for the machine failing, but to know who's going to be able to step in and resolve the situation and improve things.
So the question is, like, who's going to fix this when it fails?
Exactly. So you're not necessarily looking to blame somebody. You're looking for somebody who's going to be able to step up and say, I'm sorry, customer, that our machine rejected your application for no good reason. I've updated your account, or something like that.
Yeah. Okay. So like a contingency plan to when the AI starts presenting horror movies to people who want children's books.
Exactly. It's just the last thing you want is the machine to have the last word.
Yeah, right. And people, customer service people being on the phone saying, I can't do anything. The machine says no.
Exactly. That's the situation you need to avoid.
All right. Maybe if we just sort of still want to squeeze this in a nutshell, how are sort of the vulnerabilities with machine learning different from traditional security vulnerabilities? Like, is there like a one of those nice cookie cutter answers that I can put on a t-shirt?
I think one main difference is that if you discover a vulnerability to a machine learning model, you don't necessarily know how to fix it.
Right.
And often you don't know how to fix it. So you know there is a vulnerability, but you don't know how to fix it. So I think this is a big difference.
Yeah, exactly. Yeah. A lot of these are unsolved problems in the research community.
If I can tell that my AI is doing weird things and I can sort of figure out that, it's not looking for the tumor, it's looking for the ruler that I have in my training material pictures, is there anything that I can do at that point to sort of steer it clear of that mistake, or is it time to just burn everything and start from scratch?
It's very difficult a very difficult problem to address. Really, I think you can address it, but like it's not trivial. You need to research it, and you need really to put a lot of effort to. And once you will have fixed this problem, there might be another one that you didn't think about that will be anyway there. So it's very difficult.
Exactly. So, for instance, in that case, you could reconstruct your data set to balance out the presence of rulers or not, so that's no longer an indicator, right? And then you could train the entire system up from scratch again to get rid of that bias. But then you might have the problem that, oh no, the model doesn't work on people with darker skin colors.
Yeah, exactly. Very good example. Yeah.
And you just kind of have to keep cycling through these.
Yeah. you will always have some bias in your data, and the model will always reproduce this bias. One famous attack that has got quite a lot of attention was this poisoning of this Microsoft AI chatbot, that basically was meant to interact with Twitter users, so tweeting, retweeting, and basically interacting like this. But it was trained with already existing tweets on Twitter. And so since on social media and maybe on Twitter, we don't see the most reliable or the best content. So this chatbot became racist, sexist,
just as horrible as everybody else on Twitter is.
Exactly, in less than 24 hours, and it was taken down in that time. So this was maybe the most famous example of a poisoning attack. And here, so people didn't really know how the algorithm was working. They were just like feeding bad tweets, and it was just like integrated and learned, and then put back in the tweet that Tay was tweeting. So
I don't know. I would have wanted to be in that design meeting when somebody says like, let's train an AI model to talk like people on Twitter by showing it how people on Twitter talk. And I'm like, you want to make the bot as much of a jerk as everybody else is? Like, what is that all about?
They must have just been in the very nice parts of Twitter when they were working on this.
No, but the thing with good people on Twitter is that they have real friends on Twitter they talk to. But people who go to talk to chatbot maybe are not the best people.
Maybe I just follow like two controversial topics because I'm seeing a lot of very, very toxic behavior.
Another example that was also, so this was an attack launched by researchers, but against a real system, so against this Alexa. And basically they show that you can synthesize some sound that sound like something. So I don't know. I'm going to the store, and but there is also some hidden signal that would be interpreted by this language model that basically runs in Alexa to take on its command. So you can hide the messages in sound that sounds pretty normal to a user, but then to the machine learning model that interpret this sound, it will look totally different and launch some command that you don't intend to.
Right. And 2 weeks later, you got 22 tons of creamed corn showing up at your door.
Exactly. Some nice order on Amazon had been passed.
Yeah, I know of an instance where somebody was sitting in a taxi and it was election season, and there was a poster for a candidate with the number 120, and the car actually had this system that's supposed to recognize traffic signs. And it was looking at that and said 120 kilometers per hour must be on a freeway. That's around, 75, 80 miles per hour for you Americans?
Yeah.
But they figured that this must be a freeway because that's the only place where you get those signs.
I've seen a similar example where there was a billboard with a politician that was saying something like "Stop eminent domain abuse" or something like that. And the word stop was in huge letters. So their car kept stopping in the middle of a freeway this time. Sort of the opposite situation.
That's not what you want. Yeah, again, like, I just want to explore that so much because this, like, self-driving vehicles is one of my pet projects. And like, I'm super interested in that. And like, one of the first questions I have is like, why would that car like not take the circumstances into account? Like, you know, I'm on the freeway. There's a car in front of me that's going like at top speed. Why would there be a stop sign on the freeway when nobody else is stopping around me? Like, why would that be the case?
Because we don't know how to encode context into these things, basically. All we can do is throw data in and hope that the answer comes out. So if we throw in a bunch of data that says stop at stop signs, which you'd think would be reasonable, and it sees the word stop, it's going to think I'd better stop. And there's no way of really teaching it unless you already have like a situation where you've got like stop on billboards and that sort of thing in your training data.
That's disheartening because you would want, like, I'm playing around with sort of consumer grade home automation right now.
Yeah.
And I'm developing all these rules, like if this, then that. But there's a lot of only if this also happens and except when this is happening and stuff like that. So you'd think that like, because these are very simple rules and simple scripts. So you would think that a machine learning algorithm that's so much more complex would be able to take that on board as well. Right. But that's not the case.
It could. Fundamentally, all of these machine model learning techniques, all they do is say, generate your own list of if, then, else, whatevers, all these conditions, and then we'll tell you if it was a good list or not.
Yeah, okay.
So we have to come up with those ways of actually encoding that content, that sort of contextual information into these things if we want them to learn it.
That's a very interesting thing. So basically, it sounds to me like we're talking about developing a machine learning algorithm that seems to be doing what we sort of hoped it was doing, and then sort of fuzzing it, like just giving it like all sorts of weird random things and seeing if anything happens to break it.
Yep. And then, of course, the challenge is you have to figure out what should be the correct response in all those weird random situations.
Oh, yeah. We could start by, try not to crash and kill everyone in the vehicle. So that would be a good place to start.
It is a good strategy.
So thank you very much.
Thanks
for having us.
It was very nice.
That was the show for today. I hope you enjoyed it. Please get in touch with us through Twitter with the hashtag Cybersauna with your feedback, comments, and ideas. Thanks for listening. Be sure to subscribe.